Hello guys, so here is the second video for today and we're gonna start in chapter 21, which basically talking about the electrical potentials, and that's the mainly thing. And before we start with the material for today, try to make the connection between what we have covered in chapter 20 and what we start to cover for today. It's basically we're gonna cover electrical or electric potential and electric potential energy. Those two new terminology we're gonna cover today. Here is the connections. When we start to electrical force and we found that the relations based on the Coulomb's law depended about the Q1 multiplied by Q2 and inverse for the R square. And similarly, we're gonna talk about the potential energy, which is basically the formula. It is Q1 multiplied by Q2 divided by R. So the starting point in chapter 20 started with the force. From the force, we end up with the electrical field. And here we're gonna start from the electric potential energy, and we go to the volt or electric potential. To make this one is clear, here is the connection between chapter 20 and chapter 21. In chapter 20, starts from the force, but for the columns, and the unit it was in Newton. And from the force, we move to the electrical field concept. We mentioned it's dependent about the source of a charge. So if we have positive or negative charge here, we create the electric field based on the charge that electrical field lines will be created. And we mentioned it's gonna be very strong close to the charge and be weak and weak as far as it's far away from the charge. And the unit for this one, which is basically just the Newton per coulomb. That's for the unit for this one. In chapter 21, we're gonna start from the electric potential energy, which basically energy created from the electrical charge. And the unit it is similar for the any other energy. The energy unit it is joule. That's the unit for the potential or electric potential energy. From the electrical potential energy, gonna create what we call electric potential. That electrical potential it is similar to the electrical field, and it has some kind of the properties depending about the charge. And the electric potential it will be very high, close to the charge, and be weak and weak as far as being away from the charge. As a unit, it is basically we call it here volt, or that comes from the joule divided by coulomb, which we call this one volt. That's the connection between chapter 20 and chapter 21. Now, just a quick reminder what does that mean, or the explain some conception for the electric potential energy. Basically, if you have a charge, and that charge in this case located in the positive in electrical field, and it is also positive, and to push the charge in opposite direction of electrical field, you need to make a work, which that the concept from the electrical or the electrical energy comes from. So we need to create or generate a work. That work, let's move the positive charge from one place, certain position, a certain distance to new place, which basically calls from the low energy to the high energy or high potential energy. That's what we call the work that we have done, just the delta or delta between, or the difference between those two forces when you started and when you end up with the point that you carry the charge to. Okay. Now regarding for the mathematical formula, the relation between electrical potential, it's called V, and electrical potential energy, we give him mu. That's the formula, you keep it in your mind. Electric potential energy equal charge multiplied by electric potential. That's the relation between those two parameters or two new terminals. And as a unit for the electrical potential, we call it volt. 1 volt, it is joule per coulomb. That's the formula we are looking for. Now to imagine it or see, as we did in electrical field, the way how you imagine the electric potential values, or the strongest, or the how much I can draw it around my charge. It is similar to the electrical field. It is very strong or very high value around the charge, and keep decrease that as much as you be away from that one. So here in the first line, here is the 20 volt. The 20 volt, the entire tire, the first tire here. And you being away, move away from the charge, and that electric potential decrease. So here's the second tire's 15 volt, and here is a 10 volt, and so forth. So that's all the time the electric potential value decrease as the circles increasing around the charge, what we call the contour map. So let's see here some example regarding for how to apply this formula, how to find the electric potential energy. We're given three charges, Q1 and Q3, Q2 and Q3, and every charge located in the electric potential contours, and Q1 located at the electric potential 200 volt, Q2 at 0 volt, and Q3 at 100 volt. And ask you to find out what the electric potential energy for every charge located. So let's start from the charge number 1. We need to identify the electric potential energy. We call it E electrical 1. It's basically we have the Q1 multiplied by V1. And we have Q1. The charge is 2.5 nano, power to the minus 9 coulomb, multiplied by the volts 200. Sorry for this line. Column 200 volt. We have those two comes with this one, so we end up with the first value. It's 2 multiplied by 2.5 is gonna be 5 power to the minus 7. What the unit? Joule. That's the first electrical potential energy. The second one located in the charge number 2, we call it the Q2. It's basically Q2 times V2. And we have here is Q2, it is 2.5 power to the minus 9, power to the minus 9 times 0 volt, and this one will be 0 joule. And the third value, Q number 3 for the charge number 3, which basically Q3 times V3, and we have the charge, it is minus 2.5 power to the minus 9 coulomb times 100 volt. We end up with the 2.5 power to the minus 7 joule. That's how we calculate the electric potential energy at any charge. That's the first example. And just before I forgot it, there is the minus here. Now let's see for the second one here. And I ask you to find the electric potential energy. It is in decrease or increase. So it's we calculate the electrical potential energy at two positions. I call it, one is the At 200 is the initial positions, and the 200 is the final position. So electrical charge or electrical potential energy to move the charge from the 1 volt to the 100 to the 200 volt. What the electrical charge. So basically, we're gonna find at the end, we're gonna find the delta U, which basically here U are U final minus U initial. So we find the UI, which basically Q multiplied by voltage I, or the initial value volt. And here is the 10 power to the 9 column multiplied by the initial positions. Here is 100 volt. And we end up with the 1.6 joule, or I can type it 1.0 microjoule. For the final, it's basically the same one. The only thing is times to the 2. Here is the Q multiplied by V final, multiplied by V final, which you end up with the 2 microjoule. Okay, now delta V, U final minus U initial, you end up with the positive 1.0 power to the minus 6 joule, or the microjoule. This positive means that electrical field increase, or electrical potential energy increase. Okay. Okay. Do we have another example? Okay. So before I stop recording, we're looking for what we call the conservation of energy. We're talking about this one in 125, which basically total energy in isolated systems equal 0. Initial energy equal, or the final energy. Here is the what we call the total energy. In this situations here, we have a charge and we have electrical potential energy. That's the energy we have. Since the charge, or the electrical potential energy, responsible to move the charge from one place to another place, or from the electrical potential value to another potential value, that's lead to we have the kinetic energy. They have a charge, you move this charge. So it has a speed, it has a mass. So that's why the conservation energy that we're gonna deal with that case, kinetic energy and potential energy that we have. And the conservation of energy law, we're gonna apply it in all situations for the isolated systems. Initial kinetic energy plus initial potential energy equal final potential and kinetic energy. So that the conservation of energy. Here is the one thing before we move to the some examples here. If you move the initial position that was in high electrical potential, and you move this one from the high potential to the low potentials, and this one here is the delta V equal is the final minus initial. Final will be 400 volt minus 500 volt. So in this case, equal the delta V, or delta electrical potential, equals minus 100 volt, what we call less than 1. So if I have less than 1, and that situation is here, you basically the kinetic energy, you move the charge from the high to low. So basically you speed up in that situation. The charge will be speed up. And however, the situation is different if you are moving from the low electrical potentials to the high electrical potentials. In the same way you find the delta V, you end up here is the positive 100 volt. So I have my delta V is larger than 0, and this case, which in the kinetical energy moved from the lower to the higher, in that situation, the charge kinetical energy or the speed will be decreased. That's the two things you have to keep it in your mind. We apply some example in next video. We're gonna start from this an example how we find the final speed when I need to consider the electrical potential or conservation of energy law. Okay, let's stop recording here and let's continue in second video.